We have a very special guest from Slovenia, Professor Marko Robnik, and he's the world leader in the XAI, explainable AI. So I'm really glad that he came here, and he is going to talk about his research. Actually, he maybe developed, I don't know, maybe it's a too strong word, but SHAP values before Landberg, 2 years, or 3 years, so it was kind of a big thing. So today he's here. Today he will share his ideas, his experience with us. Please welcome him with me.
Well, thank you for a kind introduction. I'm also happy to be here for two reasons. One, that you have such a nice, great community, and the second one is that you invited me. Today I will be speaking about some of the explanation methods which we developed and which other people have developed and which make, let's say, this environment of explaining the AI. Okay, so I wanted to introduce myself. So in Slovenia we are sort of your southern cousins. University of Ljubljana is also quite a large university, but not of the size of the Warsaw University. So basically, we are I'm working at one of the faculties, it's called Faculty of Computer and Information Science. We have around 140 researchers, 1,200 students. We also have new premises, and our building is also sort of a glassy one. We have 5 undergraduate programs, 3 masters, and 2 PhD programs. So our strongest research area is artificial intelligence, which composed of machine learning, data mining, vision. We have also strong bioinformatics and intelligent robotics labs. So that's introduction. So that's what we'll be really talking about. So we will first do an overview of the explanations methods, the principle of explanation in machine learning. I will focus more on perturbation methods, and I will show 2 methods more in detail. Maybe you know them because you have here a really very successful group which works in explainable AI. Then I will explain a little bit about 2 newer methods, that's ALIGN and SHAP. And then I will show 2 use cases, one for medicine and another one for business consultancy. And I will basically finish with some unresolved issues and research opportunities. So if I try to put all that into the context, so we are working the first thing, we are working in the predictive modeling scenario. That means that we have data about, let's say, patients, and we build a model, a machine learning model. That model contains some knowledge, historical data about the patients. That model is able to predict something. And now, for example, the outcome, let's say, diagnosis for new patients, and we want to explain how this model came to that decision, because this model, for a doctor, for the user, this is a black box model, so it doesn't know anything about it. So, and we have many such models. For example, neural networks, lots of weights here, but do we know why the output is as it is? Probably not. It's like a sort of, we have many such models like support vector machines, boosting, random forest, neural networks, and to the user they are all sort of a black box. Right? So what we want to do with these methods, we want to make them more transparent, because we have Because we have many areas which are very much concerned with that transparency. For example, in medicine, with our experience, for example, physicians wouldn't want to use machine learning model unless they understand it. That's probably reasonable enough because they are really responsible for the lives of the people. But so even if the model is, let's say, statistically proven to be predictively more accurate than the physicians, they will still not want to use it. It's not the case in all the areas. For example, when we work in the business scenario or in let's say, prediction on the stock market, then people will use the model as long as it's better than what they get with other things. So it's a sort of a cultural bias of certain areas, which has its, let's say, reasons. But that's how it is. The same applies to law, consultancy, in public services, and so on. So our goal is in explainable AI is basically to have a general method which will be applicable to any predictor, and we want to explain that predictor. So let's say a few words what this model comprehensibility really means. So, for example, in decision support, model comprehensibility is basically important because in that way we'll get trust for the users. In decision support, it's known that users will be reluctant to use machine learning models. It happens nowadays in many areas. So people in offices, people in certain positions will be reluctant to use machine learning models, even if they are statistically proven to be very efficient, unless they will understand what's going on. The same applies to knowledge acquisition. For example, we want in some scientific area, if we want to show that there's some new knowledge acquired. And also, some models are supposed to be inherently interpretable and comprehensible. For example, decision trees are supposed to be comprehensible, people will tend to understand them. And it's also true, for example, for classification rules, and also linear and logistic regression are sort of comprehensible, but only to a certain degree, right? What if you have really a large tree? Will it still be comprehensible? Or if you have a really complicated rule or linear model with 100 variables, will it be comprehensible? So probably it won't be, right? So, and people have shown, I mean, I saw some papers on decision trees, for example. They have shown that really very shallow trees are comprehensible. Once they grow, let's say, over around 10 leaves, then they are no longer, let's say, there's some human cognitive, let's say, limitation which prevents us to understand more complicated models. Okay, so two levels of explanation I will talk about. First one is so-called domain level explanation. So that's something which we really would desire. So we will try to explain the true causes and effects, for example, some physical processes like gravitation and so on. So that would be really nice to have. So physicists use like differential equations and the laws of physics and so on. So for physical processes, that would be a sort of domain level explanation. And for stock exchange events, for example, we would say, okay, this company, something happened with that, and the stock went down. So that would be like domain level explanation. But otherwise, this is really unreachable for many problems because we don't know really what's going on. It's so complicated that we don't know. And in the principle, we can only hope that for some artificial problems, we have known relationship, or for example, we know the generator function, and then we can say, okay, we can reach that level of explanation. Otherwise, what do? We build some model, basically. We build some model, and then we try to understand the model. Well, that's what people do in physics. So the model explaining the movement of the planets is still a model. So we try to understand. We know the previous models were not so efficient as they people would think at that time. It probably is true also for nowadays models. So we are sort of left to the mercy of the models. So that leads us to the model-based explanation. So we have a model, for example, neural network, and we want to make that model transparent, even if at the first sight it's not transparent. So but what we can do? So what we do if you have a black box and we don't know what it does? We try, for example, poke it with the finger and see what will happen. And this is exactly what perturbation methods do. So we change a few of the inputs and see what comes out. And based on that, which inputs were poked, which inputs were changed, then we can somehow have a notion of which inputs are important, and that consists of our explanation. Okay, so in the principle, also the corrections of such explanations which will generate will be independent whether this model is correct. But for the real world, basically the better model is, for example, the better the model will explain the movement of the planets, the better we will perceive its explanation power. So basically, if we have good model level explanation, then we can say that it's also, let's say, good at the domain level explanation. So basically, in the reality, we are only interested in explanations at the model level. So, and well, we will not discuss today how to make that model really good. That would be left to the, let's say, some developer of the model. So, okay, so that's about the perturbation techniques. So basically, but in the principle, we have two flavors of that explanation techniques. So the first one is model specific. So we build some technique which is tied to the model. So we have, for example, technique which knows what this neural network does, and then it can explain based on that. For example, this is one example of a paper which basically builds a sort of parallel network. So this is the main network, and this is a parallel network used just for the explanation. And they're both trained in parallel, and then this one can explain what the other one does. So that's one way, and it's very much tied to the specific model. And another one would be so-called model agnostic explanation, which can be used for, in the principle, any predictor, but it's based on the perturbation of the inputs. As I said, we just want to poke that black box and see what comes out. So the idea of that perturbation explanation is that, let's say, for example, that we have three features, three values in our table. And these three values give us some input. So how can we proceed? What sort of explanations we get? So they together give us some prediction. Now, let's suppose that we take A away. So what happens? So there will be some change in the model, in the behavior of the model. And this, what happens, would be the contribution of A. So we took A away. If the model doesn't have the knowledge of the A, then we say this is the contribution of the A to the explanation of the model. So this is the idea of perturbation. So we will try to take A away, take B away, take C away, take the combinations of A and B away, and so on. We'll try many combinations and see what really is important. So this leads us to so-called instance level explanation. So we take one instance which we try to predict, and we'll see what really the model does. For example, I have here a model, a very simple model through so-called naive Bayes, and a very simple also a data set. So this is the data set about the Titanic ship. So people from the Titanic ship were taken, some of their characteristics were recorded, for example, the class which they were traveling in, the sex, the age, and this is one person. He was a male, he was adult, and he was traveling in the first class. And now we built a model for that, predicting whether this person survived or not. And naive Bayes said there's 50% chance that this person survived. And we can explain that. So for example, traveling in the first class was very positive for survival, while being a male was slightly negative, and being an adult was also slightly negative. So for this person, we have an explanation in a sort of, let's say, histogram. And we can build such an explanation for any person. So this is one possible explanation, right? But this is actually what, for example, medical people are interested in. So if this would be, let's say, prediction of cancer, then there would be some factors explaining which factors contribute to the cancer and which factors are, let's say, opposing the diagnosis. So this is like model-based explanation for the instances. So we take a model, in this case naive Bayes, and we explain one instance, one patient, one person here. So if you want to get really model-level explanations, what do we do? So we take lots of such instances, many instances, and we combine their explanations. And here we have such a thing for this Titanic. What do we see? For example, for the sex, we see that male was somehow disadvantageous, being female was like a positive for survival, being child was also positive, adult was slightly negative, third persons and second class travelers, this was like had a negative impact on the survival, and being in the first class or crew was like a positive thing for survival. And in this way we get like the information about the whole domain, about the whole model. So we get both in this way. So we get information on the model, the level, and the previous slide we saw explanation on the model, on the level of the instance. Okay, so so two methods I will explain briefly how do they do it. The first one, the simplest one, is called explain. So this is a sort of hides one attribute at a time. So we have a model, we hide one attribute at a time and see what happens. So so basically, in principle, we estimate the contribution of that attribute from this probability. So that's the probability of the prediction based on the instance, and that's the probability of the prediction based on the instance if we took one attribute away. So for example, the ith attribute away. So this is like a very simple approach, and this is what we get. So this was the explanation which I showed you previously. So we took one instance away from the model, and the explanations what we got were like this. They make sense. They basically explain what this model does. So this, we proposed this in 2008, for example. Maybe I can skip that because it's not that interesting. Skip that. So there's one weakness of this method. So the weakness is that we somehow hide just one attribute at a time. So for example, let's have an example. Let's suppose that we are trying to learn a simple logical function, like this one. And the model has learned it really well. So attribute 1 or the conjunction of A2 and A3. So, and now we have an instance, for example, A1, A2, and A3 all have value 1. And we want to see, for this case, which of the attributes were, let's say, which of the attributes was responsible for the prediction. We know that the prediction will be 1, right? So let's suppose that we hide one attribute at a time. So we hide A1. So the model which learned that function really well will be able to predict 1 from A2 and A3. So no problem. So it seems that A1 is not important, right? There was no change in the prediction. So now if we hide A2, so the model is still able to predict 1. So it seems that A2 is also doesn't have any impact on the outcome. And the same for the A3. If we hide A3, the outcome is still 1. So none of these attributes seems to be responsible for that. And this is the fault of that approach, because it only hides one attribute at a time. So how can we remedy that? So obviously we would have to try several combinations, right? If we would hide 2 at a time, for example, then the model would be able to predict 1 anymore, right? So basically we need, in the principle, we need all possible combinations of the attributes, so all possible permutations. And that's a lot, right? So we have 8 attributes, so we have 2 to the 8 possible combinations. And so this is what another method does. It's called IME, so interaction-based method of explanations, and it can hide any subset of attributes at any time. So basically what it says, so we will have prediction, so the contribution of any subset of features will be the difference between the, let's say, having that subset of features and not having that subset of features. So basically, one attribute will get credit for, well, for the contribution it was alone, and for the contribution in any combinations of the other features. So for example, A will get credit from being alone, for being together with the B, to being together with the C, or to being together with A, B, and C. So all combinations should be taken into account, and that will be the credit of the A, what the A gets. So what we have a problem here, I mean, that really works fine. It gives correct results. The problem we have now is these 2 to the A, right? So exponentially many combinations. So what can we do, really? So there's a solution to that proposed basically in 2009, and so okay, the contributions would be basically just all the combinations, as I said, weighted with how many interactions there were, because what we really want to do here, so this contribution of this interaction should be equally split to A and C, and this one should be assigned in equal parts to A, B, and C. Right? So this is what we want to do. So interaction with several members, each of the members should get equal share of the contribution. So, and this is basically this formula. I mean, basically it's combinatorial in how many combinations certain attributes would take place. So, and we have a simple analogy from the game theory. So in game theory, we have so-called coalitional games of 8 players. Let's suppose that these are attributes. 8 attributes are players in a coalitional game. So players form coalitions, and this would correspond to interactions. Now, the question is how to distribute the payout to the members of a coalition. For example, some coalition achieves certain goal, let's say, earn some money. So how to split that earned things to the members of the coalition. So we have one solution, which is called the Shapley value, and it's actually the unique solution to this problem of how to split the contributions. And that's unique unique solution from the Shapley, from the law of Shapley. It's called Shapley value. It's the only one which is efficient. That means that exactly splits the payoff value. It's symmetric. That means that equal payments are assigned to equivalent players. It's additive. That means that the overall credit is a sum of participating in all coalitions. And the last one is that it assigns 0 payoff to the players which doesn't contribute any. So it's the only possible, the only solution. It's like Lloyd Shapley proved that in 70s, I think. So this is what we want, right? So we want these Shapley values to have, and basically with counting all possible interactions, we would get Shapley values. But a nice thing about Shapley values is that people have been thinking a lot about Shapley values, and they have also come out with efficient sampling techniques how to compute these all possible combinations efficiently. So, so basically, as I said, Shapley value, it's what we saw before. So basically, very similar to what I have shown you previously. It's actually the same thing. So it's a coalitions, and this is the size of the coalition. So S is the size of the coalition, N is all number of players. Basically, we take all possible coalitions here, which is sort of the same as contributions here. So different persons taking part in different coalitions, different attributes taking part in different interactions. So, and as I said, it can be efficiently approximated, and this approximation is, Eric Strumberg came out with that. So basically, there's this really interesting sampling where basically it takes into account different permutations of the values, but not all permutations. We can observe how different permutations converge, how large the variance is. And based on that, we can actually stop sampling when these permutations converge. So that's why we don't have to sample all possible combinations, but only those which are, let's say, promising ones. Okay. So that's computationally feasible for, let's say, around 100 features, around 100 attributes. We get pretty good solutions here. It would be possible to improve that, but so far no one has done it. Of course, so this approach is all about sampling. How to do this efficient sampling of these subsets. So the algorithm actually is quite simple. So we choose a random permutation. So we have, let's say, initially we assign 0 to each attribute, and then we do sampling. We choose a random permutation of the features. We choose a random instance, and then we do this, as I said, Shapley-based sampling of those coalitions, and then we assign credits. And by measuring the variance of these contributions, we can determine how many samples really we need for each attribute, and that's why we can keep it linear, right? So we only need a linear number of samples. Okay, so in this way we get contributions, and this method is implemented in the R method called explain prediction. So we get what I showed you before. We'll just skip it. So another method, which is more recent, comes from 2016, has a little bit different reasoning. So the reasoning here was, if you want to do it for a really large number of instances, like thousands of features, as I said, IME, previous method, works for around hundreds of features. Then it gets really slow with all this sampling because it's not efficient enough. But if you want to do it for thousands of features, like pixels from the images or text, where we have thousands of words in the dictionaries, then we need something faster. And the solution was this so-called LIME, so locally interpretable model agnostic explanations. So the idea is that we take one instance, and then we sample the instances in neighborhood. So we sample the instances here around, and then we actually build a linear model through that. And that linear model is explanation for that instance. So for each instance separately, we sample the space around that instance and build a linear model which will tell us whether this is, let's say, a cancer or no cancer patient. So a little bit of technical details, which I won't go here into details, how to sample, how many instances to choose, how to turn them into features, even if they are numeric or non-numeric. So, but this method sort of works in practice, but has some problems, which I will mention a little bit later. So, so this is what this function optimizes. So we have a loss function which says, okay, so we want to have, what do we want here? We want that the true value of this function is close to what this linear function does, what this linear approximation does. So this is the loss, the difference between f and g. And we want that closer instances have a larger impact than those faraway instances. So this is what this pi kernel does. And we also want that this explanation is simple, so we also have a loss function which measures somehow the complexity of this model. So linear model would be very simple. Let's say SVM would be much more complex. We don't know really how to measure that. And it's actually the complexity of the model, if we follow the Kolmogorov complexity, is also incomputable, right? So there's some heuristic here. So as I said, so these are, let's say, a little bit more explained, this function. So this is what LIME tries to optimize. So it builds a linear model with this loss function. So it wants to be close to the actual value. It wants that closer instances have larger impact, and it wants the model to be simple. That means that if this model is a linear function, it means that it has to be somehow regularized. Right? So it has to throw away those features which are not that important for this prediction. So some details, maybe, as I said, samples around the explanation instance. Samples are used for training, and we use linear models typically. And then the square loss is measured local infidelity, and the number of non-zero weights in the linear model is as a measure of complexity. And then these samples are weighted with the Gaussian kernel. Okay, so there's the details. So some strengths and weaknesses of that approach. So first one is that it's faster than the IE. The second one is that it works for many features, including text and images, but it has no guarantee that the explanations are faithful and stable, because the linear model the coefficient of the linear model, which I used as explanation, can vary a lot. So for example, even if there's a small difference, the coefficient can still be large. So we have no guarantee that we will get one of those Shapley values which says that larger contributions should be given to the larger differences. So that's the downside. And also, it's neighborhood-based. We know that for the neighborhood-based models like k-nearest neighbor, there's a curse of dimensionality problem. For example, if you add one random attribute to the model might be very much off. So basically, the distances which you compute here might be problematic, because especially for those problems where we have lots of noise. So it might also not detect interactions because this linear model is too simple. So that's also possible. So we know that linear models, people who are using linear models will know that interactions have to be injected manually. Right? So we cannot test all possible interactions in linear models, so linear model might just drop many interactions. We hope that this will not happen because we are working in the local context, but we are not sure. So there's another method which tries to remedy that. It's called SHAP. It's a very recent method from 2017. Basically, it's a sort of unification of several explanation methods, including this IME, which I was talking before, and LIME. It's the method which is actually used is called kernel SHAP. It's based on the Shapley values, but these variables are using line-style linear regression. So it's faster because it uses linear regression. It's also SHAP based, but it has to be, obviously it has to be some heuristics. So this linear style heuristic this is still heuristics, right? So we don't have a perfect solution here. But some of the problems of the line are solved with SHAP. It's also faster than IME, but as I said, uses linear models with all the strengths and weaknesses. So IME is still theoretically the most supported, but this one is close to it, but because it uses like linear regression and not the original model, it might have some problems. So, for example, this is explanations which it produces. In some cases, it's better than for example, line and so on in other methods. More reliable. Okay, so that's so much about these methods which we have. In the second part, I want to talk a little bit more about how we use these explanations. I have two use cases, as I said. One is from the oncology, which I already mentioned. So here we have one explanation for the cancer recurrence. So we have a data set of the cancer patients. And the goal was, so we have cancer patients, they were diagnosed with cancers, they endured some operations, they were cured, and now the question is, will the cancer recur? It often does, but it isn't really known in which cases it recurs and in which cases it doesn't. So we built a model, so-called probabilistical RBF neural network. So that's a sort of a Gaussian neural network, right? It predicts probabilities. So radial-based function networks. And these networks work pretty well with high accuracy. So we have explanations here for one patient. For example, this one says that this patient there's 81% probability that the cancer will not recur, that the cancer will recur. And well, in this case, the patient was lucky, it didn't recur. But why such predictions? We can investigate this model and see that, for example, this factor LDI, which is like lymphatic or vascular invasion, had a very large value, so 1, so it was like on, and this is a strong factor for the recurrence. So that basically the doctors which were seeing this sort of diagrams, they agreed that they would do some diagnosis in such a way. And so, well, they trusted in a way they started to trust this model, and they were also using it as their help. For example, we can also compare different patients. For example, here we have another patient where this recurrence was estimated as very low, and we say that LDI here was 0, and that was the reason that the model say, well, it's very low probability. Indeed, it didn't recur. And the doctor again agreed that this was the strongest, let's say, decision factor here in this case. If we let's say sum together many such explanations, we get explanations for the whole domain, for the whole problem, on the level of the model, and we see that, for example, this LDI is being 0 is a strong indicator that the cancer will not recur, and so on and so forth for other values. So that's one use case. Another one, we recently used this same methodology on the business-to-business sales forecasting. So that's when the businesses sell to each other, they have like it's not like going to the shop. So they are sort of talking to the companies. They negotiate. They know each other. They know the sellers, they know the staff, and so on. So one of the companies which is active in this business-to-business sector, in IT sector, gave some data to one of my PhD students, and he was a sort of business consultant to that company. So this was the process. So he was having like workshop with those business salesmen, and they were discussing what could go wrong. He built a model, random forest model, and actually built different models, but random forests were working the best. And then he sort of showed that explanations to that people here, and they were discussing whether this model is correct, and this went on iteratively, and they improved their knowledge, they improved their feature set, they improved how they estimate different opportunities, and at the end they reached some agreement. And at the beginning they were very suspicious about how this will work, but in time when they saw lots of these explanations and when they realized that some of their intuition was wrong, so when they saw that it really helps them, they were sort of trying to be really enthusiastic, and that they are using it now in their practice. So what can people do with that? So this is a little bit more description of this data set. But what can they really do? For example, one thing they find interesting is that, well, they can just drill in and see just part of that explanation. For example, they were investigating whether if they have, for example, if the client is current, new, or past, whether does it help? So it was turning out that current, nothing surprising, but current clients were very much, for example, in favor, and upselling was also very much helping them, and so on. So they could also see which products were, let's say, more favorable to sell and which are not, and the same things for the seller. So it turned out that for some companies, certain sellers were not really appropriate. So there were some sellers which were specialized in some areas, specialized in some companies, so they were trying to do some human resource management based on that. So that was one thing. So one could also compare these two. So this one is a very simple one, and this one is much more complex, but the explanations were mostly quite similar, as we see here. So if this would be a really large data set, instead of running IME, which would be much slower, we could just run explain, which would give us, let's say, nice approximations here. So they were also trying to learn from the errors. For example, for the cases where the model was wrong, they were going into seeing why it was wrong. And for some cases, they figured out that they just don't assign the proper values to some attributes. For example, different people were estimating differently whether there is competition and so on, whether there is budget allocated at the company. So not all the sellers will have the same criteria, whether this is true or not. And this made the model less reliable. So it helped them to clean the data, for example. And they also realized that some of the data which they take into account as the users are not present in their database. So they started to collect new sorts of data from their customer management database, for example. They also did some what-if analysis. For example, what would happen if this client, for example, if we would change the seller, for example? What would happen if we would, for example, give them some discount, and so on? So this is what they were trying to sort of see what the model, the knowledge of the model, they tried to play what-if analysis. And so for many cases they could do that. And one thing which also they try to do, for example, they say, well, what if we have just new sellers, new customers? So what happens with the new customers? Not for all of them. So for example, one could bias that distribution, those instances which we select here to get the overall pictures, and they did it just for those which have the status of new clients. And it turned out that some of these explanations are very much different than from the overall database. So sort of in a business context, one can aggregate these results for the whole model in many different ways, also for the subsets. So what we really learned in that, that basically there's always an effort needed to overcome the resistance. So actually that person, that business consultant has to be present there. And that means that human in the loop was necessary. So that's one of the things which people are investigating for machine learning, when the human in the loop is needed. It was turned out in this case that it really is necessary to turn, to discuss, to clean the data, to persuade them that this is something which is useful, and also to learn them how to read these explanations. So these explanations, though we think that they are simple, were not trivial to them, right? So they were not used to read them. So when these users got some trust into the methodology, then they also wanted to use it. We also discovered that humans have many mental models, and these mental models tend to be biased. For example, when different sellers try to compare how they perceive whether the customers will be acquired or not, they turned out that they have some clear notions and some notions which are very, for example, non-data biased, as we would say. Okay, so in the end, it turned out that if we combine that what humans know and what machine learning perceive based on the history, it was like it gives the best results. Okay, so that would be. I also want to say a few things about the implementations of these methods. So we have a couple of really nice implementations. Some of the best one we produce here at this university. So for example, one of them is live R package. So this is our user group. So I think that it's appropriate if I discuss our implementations. So live is one such nice method. Basically, it's a method. It's a sort of extension of Lime. Basically, instead of just linear models, it offers several possible interpretable models. For example, decision trees, small decision trees. The other one is breakdown. It's a sort of a greedy IME. It's basically not doing the whole sampling or the whole possible subset, but it greedy samples the subset of features which tend to be useful, which could be useful, let's say. So this is the paper which describes that. I think this is maybe technologically the best what you can get in the R community for the explanations. So I think that this is like an upgrade or supplementary work to the Daleks packages, which are also authored here at this university. So it produces explanations in the form of the histograms as well. So because this is our user group, I also want to mention the method which we sort of implemented. So it's called explain prediction. It implements basically IME and the explain method. Because it also uses two other R packages, which some of them, for example, this one semi-artificial, this one generates the data from the distribution it learned from the data. I think that could be a really nice addition to what you have here, like in sampling. So maybe we skip more related work. We don't have much time left, I guess. So I would also want to speak a little bit about opportunities. So what is not good in this explanation model? So one thing I see is we need better and more focused sampling. So we have on one side, we have the method which is greedy, we have on the other side the method which tries efficiently, but still too many combinations. So maybe we can find some middle ground where this would be theoretically supported, but still more efficient what we have now. One way how to do it, as I said, we have this method explain semi-artificial, which generates much better sampling than just let's say one variable at a time sampling. So another one would be that we have better local explanation models. So we have now linear models, and we have decision trees, but I guess we could do better for some cases, because if you would do some meta learning, for example, you could really find a model which is appropriate for certain neighborhood. Maybe for some neighborhoods, nearest neighborhood will do much better. So it depends really what we. But I think that using meta learning, we could do much better than what we are doing now. Then interactions are very interesting. So in many areas, for example, we work also in bioinformatics. For example, people from the biology, they are interested in which genes would interact, for example. So these are interactions. And they want to name those interactions, not just to see that they are possible candidates. But they also want to have a form of interactions. For example, how different genes interact, in what form. So this is also, I think, quite an open research area. Then the sequences have special problems. For example, in natural language processing, we get explanations in the form of words. For example, we built a predictor for the hate speech. So whether some text is hate speech or not. Because, for example, the users of certain web portal wanted to filter those which are hate speech, right? So the model was pretty accurate. But if you want to ban some users, you have to produce some explanations for that. And explanations in the form of words, so which words contribute to that hate speech, are not enough, right? Because hate speech or any other, let's say, dialogue is much more informative than just words. We have to produce sentences. And that's true also for the other sequences. Basically, for any time series, we would have to produce better explanations, where, for example, in the form of sentences, or in the form of paragraphs, or snips of the paragraphs. Then for the images, like images are very popular now. We have really lots of neural networks which are doing great things with images. We know, for example, that there are some decision areas which one has to highlight, and there are so-called superpixels which show what, for example, what's the difference between cat and a dog. So which area are responsible for that classification. But as I said, I think there's much to do that with much to be done here. We also need better visualizations. We know that we humans have some cognitive limitations. I mentioned, for example, the decision trees are really, for example, just interpretable up to a certain degree. It's the same with the for example, the linear models. So I think that if we would be able to come out with some, let's say, meta procedure, which would say this is still comprehensible for humans and this is not, this would be like a great result, I think. And people from, maybe we should involve people from the neurology, which actually maybe understand better our cognitive limitations. So that's basically what I see as the possible opportunities for research. So if I make some conclusions, so we have basically many successful approaches, but there's lots of opportunities also for the improvements, and we know that there's a huge need for explainable AI. There are legal requirements, for example, the EU, these general data protection regulations actually requires in some cases that the models are explainable. So this is one of the reasons why people should work on that. And there's also practical need for many other models, especially in the times when we have like huge amounts of data people are collecting and don't know what to do that, then build some models and hopefully there will come something out. What will come out, we don't know, right? Because the models are complex and the models we are building today are really complex. And so, and if I conclude, basically, for some models, like some models are really difficult and we really don't have explanations, and maybe we cannot even hope to have explanations. So there's a lot of work for all of us to work on some models. So that's it.
Great, so we have time for questions. Who is going to be first? Yeah?
Can you go back to the explanation about the IME and the SHAP value?
This one,
Yeah.
or maybe
I don't know
the
if
more general one.
I understand the analogy because in the case of the IME, you analyze the 2 to the power of A elements, so all the subsets. And when it comes to the SHAP value, I think we analyze orders when the calculations are good, so factorial A. So I don't see like the direct analogy, maybe some
So basically, in the SHAP values, you have players which form some coalitions.
Yeah, but for the order, it's important. So we have slightly more cases to go through, like factorial of that. And when you only analyze the whole part, actually contributions of the A and C features, is it important? In which order they contribute? So first A or first C?
So we have different variants of this SHAP value, right? Some of them it's not the order, it's not important, for some of them it is important.
Okay.
Yeah, you're right. If you would want to take for the sequences, then we have to take into account the one which takes order into account. And I don't know of any work which would do that.
Okay, other questions? Yeah?
So I have a question about the practical use case in the medicine.
Mm-hmm.
So you said that the model was used by the doctors?
Mm-hmm. Yeah, basically they tried to use it in practice, and they I mean, the people which we were involved in, they were sort of pushing it for the diagnosis. So people at that time were using it as a substitute, to their opinion. So when we were discussing some case in the collegium, they were using also the model.
And how did it work? Because I guess that there had to be someone who understood the model and the predictions in
Right.
order to explain it to the doctors, yeah? Because it's probably too difficult, maybe not, but I guess there's some kind of a barrier there.
Yeah, you're right, of course. One of those proponents was working with us. So basically we were working with the director of the clinic, and he actually was very much interested in improving the, let's say, the prognosis of the patients. And actually he pushed it. You need a sort of, you need to have somebody who would be a promoter if you want to implement it in practice. And I think that the biggest problem in medicine is that people just don't have enough time to really do it. But once it gets really simple and it gets in their daily practice, then they start using it. So that's the obstacle. And as I said, it has to be some human in the loop. It has to be some initiative. It has to be someone who is promoted. Otherwise, it just doesn't work in practice.
Okay, thank you.
Other questions? That's great, because we have cake. Cake is waiting for us. So thank you again.